Welcome to this presentation. My name is Mark Scythian. The date today is July 31st, 2025. So in this presentation, we are going to cover DC electrical circuit design. And in this case, we're working on designing a DC parallel electrical circuit to power this motor at its specified rating. So we have a 5 horsepower rating at 1800 RPM at the motor's output drive. So that is the mechanical power. So the first step is to figure out what kind of base template we're going to use. So it's going to be parallel with one follower for the motor circuit. We have not accounted the battery yet, but first we will go to the output side and calculate the mechanical power in watts. So there's 746 watts to 1 horsepower mechanical power, so that is 3730 watts of output mechanical power. So if we divide that value into the electromotive efficiency of 72% or 0.72, we will then calculate 5180.6 watts DC electrical power is delivered into the motor, delivered to the motor from the battery. So if we access the DC electrical power formula, which is P is equal to I current amps times E volts. DC electrical power measured in wattage. We can also solve for I current by dividing the power into the DC electrical power into the voltage. And parallel circuits maintain constant voltage. Series circuits maintain constant current. So we have a current value delivered to the motor of 431.7 amps of DC electrical current. So a common mistake is to just quickly solve for the resistance at the parallel resistor by dividing E into I, because we know Ohm's law says E, voltage, is I times R. So going right to Ohm's law and solving for resistance or voltage divided by current will initially solve for the uncorrected metrics from the battery. So we haven't accounted for the dissimilar voltage and current from the battery. So it's good to gain that practice, make the mistakes, and then correct yourself thereafter. So if we were to approximate 5% more current, or just initially 10% plus or minus 10% current, we could quickly find a value somewhat greater, but we would go down to the acceptable 5% plus or minus current delivery and calculate a good mathematical schedule of what the base resistance would be, but we still haven't corrected for the battery's source specification. So this is more like a practice. So we can get rid of this and just put these incorrect values in for now. Now go to the source instead of the output. We'll go to the source now, the potential energy. We actually have to take away 3.5 volts so that 12 volts is delivered into the circuit. So now we can use Ohm's law set up for its original voltage metric of E is equal to I times R. So E is the voltage. We have to drop 3.5 volts on series. So we can make that equal to 2000 amps from the battery times R and simply solve for R. So we get a resistance value on the first resistor on series of 0.00175 ohms. And then we actually have to drop the current on parallel. Because remember, we get voltage drops on series, and here we get current drops on parallel. So we actually have to recalculate that resistance value. So the parallel resistor is going to drop 1568.3 amps of current. So this time we just divide the E into I to get R. So we calculate 0.00765 ohms at 12 volts on the parallel resistor. And remember, in the real world, this would be a digital resistor. These would be digital programmable resistors, and more than likely a pulse width modulator, a PWM. So instead of using traditional analog resistors, which simply dissipate the current and voltage in the heat, depending if they're on series or parallel, the PWM would simply just send 1568.3 amps back to the source, and allowing only for 431.7 amps to extract out of the parallel circuit and follow from positive to negative. So we're positive to mid circuit and then to negative. It's back to source. So again, what goes in comes out. So we have our 431.7 amps going to ground. We have our 3.5 volts drop on series. And then we have our 1568.3 amps current drop on parallel. That leaves us with 431.7 and our 12 volt parallel circuit to the motor. So we can just finalize and finish this up, connect this together. So now we're complete. We've succeeded in designing a DC parallel electrical circuit to power motor at specified rating, and then we have our on-off switch here. So when we turn the switch on, we're going to send the electrons to ground. Everything's going to flow for the battery. Battery puts 15.5 volts DC 2000 amps in, but then it loses 3.5 volts on series, making it 12 volts. 12 volts then flows to parallel, divides itself into this 0.00765 ohms resistance, then drops 1568.3 amps of current back to source, leaving 431.7 amps to go to the motor, go through the motor. Of course, we have a 12 volts transferring also to the motor, then flowing to ground, completing the circuit. Thank you for watching this presentation and have a great day.